So hello everyone, in this video we will be discussing limit theorems and one-sided limits. So to recall or refresh what you've learned so far in Math 21, consider the functions f of x and g of x that are defined on some open interval containing a, except possibly at a. The following propositions hold. 1. If the limit of f of x as x approaches a exists, then it is unique. If C is an element of all real numbers, then the limit of C as x approaches A is equal to C itself. For any value of A, which is an element of all real numbers, the limit of x as x approaches A is equal to A. Suppose the limit of f of x as x approaches A is equal to L1, and the limit of g of x as x approaches A is equal to L2, where L1 and L2 are elements of all real numbers, and C is an element of all real number, then the limit of the sum or difference of f of x and g of x as x approaches A is equal to the sum or difference of L1 and L2, or the individual limits. The limit of C times f of x as x approaches A is equal to C multiplied by the limit of f of x, which is L1. The limit of the product of f of x and g of x as x approaches A is equal to the product of L1 and L2. The limit of f of x over g of x as x approaches A is equal to L1 over L2, given that g of x is not equal to 0 on some open interval containing A except possibly at A, and L2 is not equal to 0. The limit of f of x raised to n as x approaches A is equal to the limit of f of x, which is L1 raised to n, for some value of n, which is an element of all natural numbers. The limit of the nth root of f of x as x approaches A is equal to the nth root of L1 for some value of n, which is an element of all natural numbers, with n greater than 1, and given that L1 is greater than 0 when n is even. So, as a consequence of the above limit theorems, if we let f be a polynomial or a rational function, and a be an element of the domain of f, then the limit of f of x as x approaches A is equal to f of A. So, it's just a simple substitution if the given is a polynomial or a rational function, and A is an element of the domain of f. Right. So this theorem lets us substitute values directly to the limit without breaking it down to multiple limits. So sometimes it's not possible to just directly substitute the values to the function. So such limits where we cannot determine its value are called indeterminate forms. As an illustration, if we let the limit of f of x as x approaches A be equal to 0, and the limit of g of x as x approaches A is equal to 0, then the limit of the ratio f of x over g of x as x approaches A is called an indeterminate form of type 0 over 0. Then we deal indeterminate forms via other methods, so we can't use the direct substitution in this situation. So the first method is factoring. This usually invoked when given rational functions that result to 0 over 0, where one could cancel common factors. And the other method is rationalization, usually invoked when there are radicals in either numerator or denominator, where one would eliminate them by multiplying by the conjugate. So first problem or example, evaluate the limit of the square root of 8 minus x squared minus 2 all over 6 minus square root of x squared plus 8x plus 16 as x approaches 2. So yung una mong gagawin ay try mo munang i-substitute yung 2 sa function. We start by recognizing that the limit is an indeterminate form of type 0 over 0. So, paano niya yung nagawa? Sinubstitute niya muna yung 2 sa function 8 minus 2 squared minus 2 all over 6 minus 2 squared plus 8 times 2 plus 16. So yung lalabas ay 0 over 0. So we can't obtain the limit directly from substitution. Then observe that the numerator is simpler to manipulate, so we rationalize square root of 8 minus x squared minus 2 by multiplying the numerator and the denominator by its conjugate to get. So after multiplying this function by its conjugate, we get the limit of 8 minus x squared minus 4 all over the quantity x 6 minus square root of x squared plus 8x plus 16 multiplied by the square root of 8 minus x squared plus 2 as x approaches 2. So simplifying further the numerator, so we get this bottom function. Splitting the limit of a product into product of limits, we have so what we did here is we split the function, the original function, into two. So this is a rule discussed earlier. So the limit of f of x times g of x is equal to the limit of f of x times the limit of g of x. So for the second function, for the second expression, the limit of 1 all over the square root of 8 minus x squared plus 2 as x approaches 2 can be easily evaluated using direct substitution. So after substitution, we get the limit of 4 minus x squared all over 6 minus square root of x squared plus 8x plus 16 multiplied by 1/4. So this 1/4 is the limit of the second function. So you can also try substituting 2 to the first function, but it seems that the resulting answer would be 0 over 0. So we use rationalization, rationalize the denominator by the conjugate 6 plus x squared, the square root of x squared plus 8x plus 16. So simplifying further, we get the limit of the quantity 2 plus x times 2 minus x multiplied by 6 plus square root of x squared plus 8x plus 16 all over 2 minus x times x plus 10. So you can notice that there is a common factor from the numerator and the denominator, which is 2 minus x. So cancelling this, we get a limit of the quantity 2 plus x times 6 plus square root of x squared plus 8x plus 16 all over x plus 10. So if we try the direct substitution, we can see that it will not result to a 0 over 0 or an indeterminate form. So substituting it, we get 48 over 12, which is equal to 4. So just remember that 4 is just the limit of the first function. So therefore, the limit of the original function as x approaches 2 would be equal to 4 multiplied by 1/4, which is equal to 1. So this is the final answer. So for problem 2, evaluate the limit of the cube root of x minus 2 all over the square root of 9 minus x minus 1 as x approaches a. So you can try direct substitution. The numerator will be 2 minus 2 all over the square root of 1 minus 1, which is equal to 0 over 0. Yeah. So we can rationalize the numerator by introducing a factor that will make it in the form a cube minus b cube to eliminate the cube root for some value of a and b, which is an element of all real numbers. So you can just recall this identity. This was discussed in, I think, junior high school. So a cubed minus b cubed is equal to the quantity a minus b multiplied by a squared plus ab plus b squared. So we can let a be equal to cube root of x and b be equal to 2. So we get a squared plus ab plus b squared, which is equal to the cube root of x squared plus 2 times the cube root of x plus 4. So we can use this to rationalize the numerator. After multiplying the numerators and the denominators, we get the limit of x minus 8 all over the square root of 9 minus x minus 1 times the quantity cube root of x squared plus 2 times the cube root of x plus 4. So we will again split the limit of a product into product of limits. So we have the limit of the original function as x approaches 8 be equal to the limit of x minus 8 all over the square root of 9 minus x minus 1 as x approaches 8, and the limit of 1 all over the cube root of x squared plus 2 times the cube root of x plus 4 as x approaches 8. You can try substituting 8 to both expressions. For the second function or expression, by substituting 8, we get 1 over the cube root of 8 squared plus 2 times the cube root of 8 plus 4. And for the first function, we will get 8 minus 8 all over 9 minus 8 minus 1, which is 0 over 0, which is again an indeterminate form. So simplifying this, we get the limit of x minus 8 all over square root of 9 minus x minus 1 multiplied by 1 over 12. So 1 over 12 is the limit of the second function. So to find the limit of the original function, we will need to find the limit of the first function in this product. So we will again rationalize the denominator to get the limit of x minus 8 multiplied by the square root of 9 minus x plus 1 all over 9 minus x minus 1. So we will just multiply the numerator and the denominators. So simplifying, we get x minus 8 multiplied by the square root of 9 minus x plus 1 all over 8 minus x. So you can notice that there is a common factor in the numerator and the denominator. So if you factor out the negative sign in the numerator, you will get negative times negative 8 minus x multiplied by the quantity square root of 9 minus x plus 1 all over 8 minus x. So you can cancel 8 minus x from the numerator and the denominator. So the resulting function will be negative of square root of 9 minus x plus 1. So substituting 8 to get negative square root of 1 plus 1, which is equal to negative 2. So the limit of the original function, which is the cube root of x minus 2 all over square root of 9 minus x minus 1 as x approaches 8, is equal to the product of negative 2 and 1 over 12, which is equal to negative 1 over 6. So for the last problem, evaluate the limit of the absolute value of 5x squared plus 3x minus 2 minus the absolute value of 2x squared minus x minus 3 all over x raised to 4 minus 1 as x approaches -1 from the right. So recall the property of the absolute value function. So an absolute value function can be written in a piecewise function. So the absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. So these are properties that are concepts that you should know from junior high school. So from this, we see that if we use this property to the problem above, we get the absolute value of 5x squared plus 3x minus 2 be equal to this piecewise function. Solving the quadratic inequality, one obtains the explicit conditions of x. So if we solve these inequalities, we will get this piecewise function. So the absolute value of 5x squared plus 3x minus 2 is equal to 5x squared plus 3x minus 2 if x is less than or equal to -1, or x is greater than or equal to 2/5. Or this function can be equal to negative quantity of 5x squared plus 3x minus 2 if x is greater than -1 but less than 2/5. So doing this to the other factor or to the other expression, we get this piecewise function. So as x approaches -1 from the right, that is, x approaches values arbitrarily close to -1, but greater than -1, the limit then becomes the limit of negative 5x squared plus 3x minus 2 minus negative quantity 2x squared minus x minus 3 all over x raised to 4 minus 1 as x approaches -1 from the right. So paano nakuha tong expressions na to? Going back to this slide, at values of x greater than -1, so from the right, we will use this expression here. So similarly, for the absolute value of 2x squared minus x minus 3, at values of x greater than -1, we will use this expression here. So going back to the solution, we can simplify it to negative 3x squared minus 4x minus 1 all over x raised to 4 minus 1. So every step of the way of the process, you can try substituting -1 to the function and see if the answer would be an indeterminate form, or it can be solved using direct substitution. But in this case, substituting -1, we will get -3 plus 4 minus 1 all over 1 minus 1, which is still equal to 0 over 0. So you can use factoring, the method of factoring to solve this limit. You can't use rationalization because obviously there's no radical sign here. So factoring the denominator, we get x squared minus 1 and x squared plus 1. And factoring the numerator, we get negative 3x plus 1 and x plus 1. So since there's still no common factor from the numerator and the denominator, you can still factor x squared minus 1 into x plus 1 and x minus 1. So you can now cancel x plus 1 from the numerator and the denominator. So the resulting expression will be the limit of negative 3x plus 1 all over x minus 1 times x squared plus 1. So we can try direct substitution. So we will get negative 3 multiplied by negative 1 plus 1 all over negative 1 minus 1 multiplied by negative 1 squared plus 1. So simplifying, we get negative 1 half. So the limit of this tedious function is just negative 1 half. So we solve this problem by using the property of an absolute value function and multiple factoring. So if nag-exam ka and gumamit ka ng factoring method pero wala kang nakitang common factor, you can still inspect the resulting function and look for expressions that can still be factored. So malay mo, may lumabas after another factoring process. So that's it for this video.